So can I start?
Yes. Yeah. Okay. Professor Hirano will speak on equivariant tilting modules and Papian varieties and non-commutative matrix factorization. Okay, please.
Thank you for introduction. And I would like to thank the organizers of this object geometry in East Asia seminar. Today, I want to talk about equivalent tilting modules and Papian varieties and non-commutative matrix factorizations. Today's talk, tilting object is one of the key notion. So let me first recall the tilting object.
Excuse me, I think you need to share your screen.
Yeah, of course, yes. Sorry.
Thank you very much. Oh yes, so now we see
yes.
The screen. Thank you, thank you very much.
Okay, yeah. And so I recall the definition of tilting object. So let A be a abelian category with small coproducts. So this is e.g. A can be taken as quasi-coherent shifts on some scheme X, or the modules over some ring R. R is not necessarily commutative. So then object in an object T in A is tilting if the following three conditions are satisfied. The first condition is extension group, ith extension group of T is 0 for any non-zero I. And the second condition is T is compact. I don't give a precise definition of a compact object, but if A is a quasi-coherent shifts on some scheme, then the second condition 2 is equivalent to T is a perfect complex on X. And the perfect complex is a subcategory of derived category of coherent shifts, which is consisting of bounded complexes of vector bundles on X. So in particular, if T is a vector bundle, then T is compact. And the third condition is that T is a generator of unbounded derived category of A. And again, I don't give a precise definition of a generator, but if A is a quasi-coherent shifts on X, this third condition is equivalent to T, the smallest triangulate subcategory containing in T is equal to perfect complexes. And if the first two conditions are satisfied, we say that T is a partial tilting object. And the following proposition is classical. So let X be a smooth variety, and let T be a partial tilting bundle on X. And assume lambda, this is defined to be the endomorphism ring of T. this ring is of finite global dimension. And write add T for the subcategory of coherence shifts consisting of direct summands, all direct summands of finite direct sums of copies of T. So then we have an equivalence between the bounded homotopy category of add T and bounded derived category of finitely generated modules over lambda. And moreover, if T is tilting in quasi-coherent shifts, then we have an equivalence between bounded derived category of coherent shifts and bounded derived category of finitely generated right modules over lambda. So this is a classical result, and there are many known examples of variety which admits tilting bundle. For example, the famous example is projective space, and other many examples are known. But if X is projected Calabi-Yau variety, then X never admit tilting bundle by a cell duality. So the first result of this talk is generalize this classical result to matrix factorizations. So more precisely, we generalize the above proposition by generalizing tilting bundle to G equivariant tilting bundle. And here G is some algebraic group acting on X, and also by generalizing a bounded derived category of coherent shifts on X to derived matrix factorizations of XWG. And this is called gauged Landau Ginsburg model. And X is a variety, and W is a regular function on X, which is a semi-invariant with respect to G action. And so we show that G equivariant tilting module, the tilting bundle on X induces an equivalence of derived matrix factorizations. And later I will explain more precise statement. And this is the main result of this talk. And second result is the application of this first result. So applying one, we show the following. So let V be a vector space of dimension D, and let Q be a non-negative integer such that this condition is satisfied. And let PFQ be a Pfaffian variety. This is defined this way, in this way. And this variety is sometimes this variety is smooth. For example, PF1, this is nothing but Grassmannian. So this is smooth variety, and also PF 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 this is a whole space. So this is also a smooth variety, but usually Parthian variety is highly singular. But if we can consider a linear section of Parthian variety, then we can get a smooth one. So let L be a subspace such that with selection to L, which is defined to be an intersection of Parthian variety and projectivization of L is smooth. So the second result is as follows. So there exists a non-commutative gauged Landau-Ginzburg model. I will give a precise definition later of this notion. But yes, and there is this non-commutative gauged Landau-Ginzburg model, lambda WGM, such that we have an equivalence between bounded derived category of coherent shapes on the linear section PFQL and derived factorization category of the LG model. So this is the application. So sometimes this linear section can be smooth Calabi-Yau variety. And as I said, smooth Calabi-Yau variety does not admit tilting bundle. So bounded derived category of project Calabi-Yau variety is never equivalent to derived category of non-commutative ring. But if you consider derived factorization category, we can apply some representation theory of non-commutative ring to study derived category or coherent shapes on projective Calabi-Yau variety. And there is a previous related work by Okonek-Telemann. So Okonek-Telemann shows that a similar result for completed section in some project space. Yes, this is our main results. So next, I will recall some elementary definitions. So first, I will recall some notion of equivariant algebra and equivariant modules. So let G be a linear algebraic group acting on some scheme X. Then an OX algebra is a sheaf of algebras A on X with a morphism of sheaves of algebras rho such that its image is in the center of A. And also A can be seen as a OX module, and we require that A is a coherent OX module. This is the definition of OX algebra. And G equivariant OX algebra is a pair A and theta A. And A is a OX algebra. And theta A is some isomorphism of sheaves of algebras on G cross X. So here, pi and sigma so pi is a projection, and sigma is G action. Such that the pair A theta A is a G equivariant OX module. So this means that the isomorphism theta A satisfies a suitable cocycle condition. But I don't write a precise definition. But yes. And third definition is equivariant module. So a G equivariant A module is a pair M theta M, and M is a right A module such that M is a quasi-coherent sheaf on X. And theta N, this is isomorphism of pi upper star A modules. And this pair and this pair defines G equivariant OX module. So this is the definition of equivariant modules. So then we can consider QCOF GA. This is abelian category of G equivariant A modules. And we also consider subcategory of G equivariant coherent A modules, denoted by COH GA. So I will show some examples of equivalent algebra or equivalent modules. So first example is a trivial one. So namely, if some algebraic group G acts on X, OX is a G equivariant OX algebra. And QCOH G OX is nothing but usual G equivariant quasi-coherent sheaves on X. And second example is that if F is a G equivariant coherent sheaves, then a sheaf of endomorphism algebra of F is a G equivariant OX algebra. And also, this sheaf F induces a natural functor from usual equivariant quasi-coherent sheaves to quasi-coherent A modules, equivariant quasi-coherent sheaves, equivariant quasi-coherent A modules, and which is given by Hom F. Okay, and also similarly to usual quasi-coherent sheaves, we can define direct images, inverse images and tensor products of equivariant modules. So, so now I will recall a definition. I introduce definition of equivariant tilting modules. So let X be a variety, and let G be an affine algebraic group acting on X, and let H be a closed normal subgroup of G, and let A be a G equivariant OX algebra. In this setting, and let T be a G equivariant coherent A module. Then we say that T is GH tilting if and only if restriction of T to H is a tilting object in quasi-coherent H equivalent quasi-coherent A modules. So here, rest-GH is a restriction factor. So here, rest-GH is a restriction. And we say that T is partial GH tilting if and only if the restriction of T is partial tilting object. So now I introduce equivariant version of derived Morita equivalence. So let spec R be an affine normal variety with G action such that H action, which is induced by G action by restriction, is trivial. And let F be a morphism from X to spec R, which is G equivariant morphism, such that since H action is trivial on spec R, we have F induces a morphism F bar, which is from quotient stack X over H to spec R. And the condition is F bar is proper morphism. And let T be a G equivariant coherent A module, and let lambda be a endomorphism ring of T. Since lambda is isomorphic to this one, namely direct image of sheaf of endomorphism algebra of T by F. So lambda can be seen as G equivariant R algebra. So then we consider the following composition of functors, and we denote by F. So F is a composition of home T, composition of home T, and taking H invariant part. So then we have a functor from this to this. And the following theorem is equivalent version of derived Morita equivalence. So assume G over H is reductive, and also assume that global dimension of lambda H. So lambda H is a H invariant part of lambda. So global dimension of lambda H is finite. And the first claim is that if T is partial GH tilting, then right derived functor of F defines an equivalence between bounded homotopy category of add GT and bounded derived category of finite degenerated modules over lambda H, which is G over H equivariant. So this is the first statement. And moreover, if T is GH tilting, then this right derived functor induces an equivalence between bounded derived category of G equivariant coherent A modules and bounded derived category of finite degenerated G over H equivariant lambda H modules. So this is already a generalization of the result in the in this proposition. So we equivariantize of this proposition and to get this theorem. But our main goal is to generalize the result to matrix factorizations. And so I will introduce the notion of matrix factorizations. So matrix factorizations are defined for Landau-Ginzburg model. So let me start recall the definition of gauged Landau-Ginzburg model. So gauged Landau-Ginzburg model is data AWG, and G is an algebraic group acting on X, and X is a scheme, or X can be a stack, algebraic stack. And A is a G equivariant OX module, OX algebra. And W is a semi-invariant regular function on X. And here, semi-invariant means that there exists a character of G, chi, such that W of Gx is equal to chi G times Wx. And if the OX algebra A is non-commutative, then sometimes we call AWG non-commutative gauged Landau-Ginzburg model. So for gauged Landau-Ginzburg model, a factorization of this LG model is a sequence F, which consists of F1, F0, and phi1 and phi0. And each Fi is a G equivariant coherent A modules. and each phi I are G equivalent morphisms such that compositions of phi I are multiplication by W. And here F1 chi, this is defined to be a tensor product of F1 and O chi. O chi is a G equivalent line bundle induced by the character chi. And chi is this character chi. And if each Fi are locally free, then F, the factorization F, is called matrix factorization of the AGEA model. Then we define some triangulated categories. So since we can consider factorization as two periodic complexes, but the usual complex is the composition of differential is 0. But in this case, the compositions of phi I are W, multiplication by W. So in this sense, factorization can be considered as a twisted complex. And for twisted complex, we can consider the morphism of factorization similarly to the usual complexes. And also we have notion of homotopy equivalence of morphisms of factorizations, which is also similarly defined to usual homotopy equivalence of morphisms of complexes. So then we write K conf G AW. This is the homotopy category of factorizations. So yes, so the objects are factorizations, but the set of morphisms are equivalence classes of homotopy equivalences. And then we define derived factorization category as a Verdi quotient of homotopy category by A conf G AW. I don't give a precise definition of this category, but this category consisting of acyclic factorizations. And acyclic factorization is analogy of acyclic complexes. So derived factorization category is analogy of usual derived category of complexes. And if algebra A is OX, then we write D conf G XW. And sorry. And if X is affine and A is a global section of algebra A, then we write a D mod GAW for D conf GAW. And we explain derived factorization category is a generalization of usual derived categories. So consider the trivial GM action on the variety X. So then we have an equivalence between bounded derived category of G equivariant coherent A modules and dec of G times GM A0. And this functor defined in this way. So the complex FD, the D is a differential, is mapped to factorization of this form. And it is easy to see that this natural functor is an equivalence. So now we are ready to explain more precise statement of the main result. So let X be so far. Is there any questions?
So what is chi in the last term of the complex?
Yes. Thank you. Yes. Chi is a projection of from G times GM to GN. Thank you.
Yeah, thank you.
Yeah. So the setting is the following. So let X be let X and the spec R be varieties with G action, and let H be a closed normal subgroup of G, such that H action on spec R is trivial. And let F be a G equivalent morphism from X to spec R, such that induced morphism F bar is proper. And let WR be some semi-invariant regular function on spec R. And let define WX to be the F upper star WR. This is also a semi-invariant regular function on X. And let A be a G equivariant OX algebra, and let T be a G equivariant coherent A module, and write lambda for the endomorphism algebra of T. So in this setting, the main result is the following. So first, assume that G over H is reductive, and global dimension of lambda H is finite. The first statement is that if T is partial GH tilting, then the similar functor to the above, similar right-derived functor over F induces an equivalence between K add G T WX and D mod G over H lambda H WR. And here, K add GT WX is defined to be a subcategory of homotopy category consisting of factorization F, such that each Fi is in add T. So namely, the subcategory of direct sums of T. And second, if T is GH tilting, and if a injective dimension of all equivalent coherent A modules are finite, so then the same factor, the same derived factor induces an equivalence between derived factorization categories. So this is the main result, and this is a generalization of the classical result, which is appeared early in this talk. So now let me explain application of this main result. So to explain application, I need to introduce some notion, namely non-commutative resolutions. So let X be a normal variety. So then a non-commutative resolution, which is abbreviated by NCR, a non-commutative resolution of X is an OX algebra of the form sheaf of endomorphism algebras of some M, such that global dimension is finite. And here, M is a non-zero reflexive coherent sheaf on X. So if F is a resolution of spec R, and if T is a tilting vector bundle on X, such that its endomorphism algebra is of finite global dimension, then we have lambda. This lambda is an NCR of R. And as we saw above, the bounded derived category of coherent sheaves is equivalent to bounded derived category of finitely generated lambda modules. So so X can be seen as a commutative resolution. On the other hand, lambda is a non-commutative resolution of spec R, and these are related by equivalence between derived categories. And once we have this equivalence, we can study derived category of coherent sheaves by representation theory of non-commutative rings. So I introduced one of the best results for non-commutative resolutions. So this is by Spenko and Michel Vandenberg in 2017. So assume the field, base field is algebraically closed and the characteristic is 0. And let G be a reductive affine algebraic group acting on smooth affine variety. And assume that XS, this is corresponding to smooth locus in the quotient, which is defined to be a point X such that orbit of X is closed, so closed orbit, and stabilizer of X is trivial. And this set is not empty, and the codimension of a complement of XS is greater than or equal to 2. So then there exists a non-NCR of affine quotient of X by G. So this is the introduction of non-commutative resolutions. So let me explain a precise statement of the second result. So base field is now complex numbers, C, and let V be a vector space of dimension D, and Q is a non-negative integer such that satisfy this condition. And let Q omega be a symplectic vector space of dimension 2 times Q. And let GSPQ, this is the similitude symplectic group, and defined to be in this way. So this is a subgroup of affine subgroup of general linear group, and this GSPQ is isomorphic to the semi-direct product of usual symplectic group of Q and GM. This corresponds to diagonal matrices. And let Y be a homomorphism, linear maps from V to Q, and consider GSPQ action on Y. This is naturally defined by composing this element with this element. So we have a natural action, and let P is a morphism from Y to PFQ F. This is a affine cone of Parthian variety, and this is a closer variety of this affine space. And P is defined to be defined by mapping phi to phi upper star omega, and omega is the symplectic form on the Q. So then P in this is morphism from this quotient stack to Parthian variety. And since this stack is smooth, so we can consider this map is a commutative resolution of Parthian variety. And recall that irreducible representations of symplectic group is one-to-one correspondence to Young diagrams of height at most Q. And when consider a subset, this is a subset of this of width at most S, and S is defined by this. And we write YQS corresponding to this subset under this correspondence. So for gamma in this set YQS, for this representation, we can choose irreducible GSPQ representation. We denote by V gamma, such that the restriction of V gamma is in YQS. And set T So define T to be a direct sum of V gamma, and the gamma runs over YQS. This is coherent shifts on the stack Y. So Y is this stack. Yes, and actually this coherent shifts on Y is equivalent to GSPQ equivariant coherent shifts on this space. So GSP representation defines some equivariant shift in this category. So then B, this is a direct image of endomorphism, a shift of endomorphism of T by the morphism pi. This is a non-commutative resolution of Parthian variety. And let L be a subspace such that a linear section of Parthian variety is non-empty. So then the restriction of B to L is a non-commutative resolution of linear section of Parthian variety for choosing generic L. This follows from a non-commutative version of Bertini theorem. This theorem is proved by Rennemo, Segal, Schiff-van-den-Berg in 2019. And let W be a Y cross L pub, and L pub is the vanishing locus of L. In the this is in the dual space of original wedge to B star. And consider GSPQ action on W defined by this. So our second main result, second result is the following. So there exists some non-commutative gauge LG model, lambda WGM, such that bounded derived category of coherent BL modules is equivalent to the derived factorization category of the gauge LG model. And the ring lambda is a non-commutative resolution of quotient of W, affine quotient of W by GSPQ. In particular, if the linear section is smooth, this category is equivalent to the usual derived category of coherent shifts. So we get this equivalence. So I introduce, I will explain a rough sketch of proof. So first, I define the regular function W by this way. So W is a regular function on Y cross L pub, and this is GSPQ invariant. And define additional GM action on this space by this. And let U be open subspace of Y. So then we have this non-commutative gauge LG model. And then we have a equivalence between this category and this category C. And C is a subcategory of this category defined by this way. So C is factorizations such that each restriction of each Fi is YQS. And also, they exist. We see that there exists some partial GM times GSPQ tilting such that C, the category C, is equivalent to K add GM times GSPQ TW. And this is a subcategory of this category. So by main result, this category is equivalent to this category. So we get equivalence between C and this. And C is equivalent to this category. So we obtain an equivalence of this equivalence. So so I stop here.
Okay, it's nice talk. So any question or comments?
So I'm kind of curious that why you call it Landau-Ginzburg model?
Sorry, where?
So why is the name?
Name?
Yeah.
Landau-Ginzburg.
Yes.
This is I think this is from physics, but I don't know the background of physics, so sorry, I don't know.
So can you explain other version of physics, the Landau-Ginzburg model?
Sorry, I don't know the physics. Sorry.
Excuse me.
Yes.
May I have a question?
Yes. Yes.
Yeah. So the reductive condition, or you
Yes.
assume the reductive condition for the equivariance theory.
Yes.
How is the effect of the reductiveness of the
reductiveness? Yes. Thank you. So we use reductiveness.
Yeah.
Yes. So the one of the key effect is that if G is reductive, then restriction factor. Well, maybe more precisely, if G over H is reductive, then restriction factor from G to of Hx. This is a exact factor. This is exact. So this is a key point, I think.
Okay, thank you.
Yes. And also this is also faithful factor.
Yes, I have. Okay.
Okay. Any other question?
Yes. Can I ask a question?
Yeah.
Yes, I think could we generalize the, for example, the global Cauchy case to the, for example, smooth dimensional stack with local orbifold structure? For example, you write a restriction function, and
yes.
Is it possible to consider locally in a global picture and which has a left join and the right join?
Yes, yeah.
Is it possible?
Sorry, sorry, I couldn't understand your comment.
Sorry, could
Sorry,
you?
Yes.
Yes, should I repeat it? So should you generalize your result to the global quotient from the global quotient to the smooth dimensional stack with local orbital structure?
Generalize this theorem.
Yes, you can.
Maybe I think so, but I don't check that. But but I think so. You want to consider some stack?
Yes, for example, we consider the smooth stack associated to the variety with a quotient singularity.
Yes, but so if stack is a quotient stack, then I can apply this theorem. But I don't know we can generalize this theorem to arbitrary stack.
Yes, another question is,
Yeah,
you can to show the restrict function in the.
Yeah.
Yes, and in the global quotient, for example, a smooth variety quotient of finite group, we have a restrict function from the.
Yeah.
For example, it has a left joint and the right joint, and we can realize it as a product. And could we generalize this result to the, for example, the smooth dimensional stack?
Smooth dimensional. I think so. But
So,
I didn't check.
Yes, but I. Yes. Yes. So can you explain a little about how to generalize it to the global?
How to generalize this because this proof are very categorical. So
yes.
So I think and the quasi-coherent shift on Drinan Marford stacks very share some nice properties of usual quasi-coherent shifts on the smooth varieties. So yeah, I think many of the arguments works for Drinan Marford stacks.
Yes, I see. Thank you very much.
I have a question, one more. Okay.
Yes.
So the non-commutative, from the definition of the non-commutativity resolution, the non-commutativity is naturally implied from the conditions.
Sorry,
Non-commutativity of M is naturally implied or induced from the condition of the definition.
And the condition of M?
Yeah, M. So you so explicitly mentioned the non-commutativity of M, but it is so naturally induced. So the non-commutativity of M. Oh, that is so concerned with the definition of the.
Yes. Yes. Of course. Yeah. If yes. So yes. If X is smooth.
Yeah.
If X is smooth, then OX is nothing but shift of endomorphism algebra of X. So in this case, this is commutative. So this definition is essential in if X is singular. So in general, this definition does not imply A is non-commutative.
Yes, but what is so naming of this non-commutativity?
Naming is that usually this algebra is non-commutative algebra.
Yeah.
So we say this non-commutative resolution.
Yeah. Okay.
And,
Thank you.
Yeah. Yes.
So I think it's time to wrap up. So let's thank the speaker. Okay.
Thank you.
So okay, I'd like to thank the speakers and all the participants, and hope to see you all in 2 weeks later. Okay, bye now.
Bye. Thank you.
Bye.